Hi, in this lecture we will have a look at one of the most famous graph algorithms, the Dijkstra algorithm, used to solve the problem of path finding. Solving this problem means finding the lowest cost route from one node to another in a graph. Depending on the problem, lowest cost might mean different things. For example, in the shortest path problem, the cost is the length of the route. In that case, the weight of the edges might correspond to the length of a road. Sometimes, instead of finding the shortest route, you want to find the fastest one. In that case, the weight of the edges might correspond to the level of congestion of a road or an estimation of the time it takes to traverse that road given the traffic conditions. Well, let's start by understanding the idea behind Dijkstra algorithms using an example. We will use this small graph to show the workings of Dijkstra's algorithm. For this example, we are going to find the lowest cost route from node A to the rest of the nodes. The graph might represent 5 towns connected by roads, and the numbers close to the edges might represent the length of each road. The first step executed by Dijkstra's algorithm is the initialization of a table where the routes from node A to every other node will be recorded. The first column of this table is the destination node. Remember that the start node is node A. So, in this table, we will record the information necessary to go from A to any other node using the shortest path. The second column is the distance of the shortest path from A to the destination node. At the beginning of the algorithm, you can think of yourself standing at node A. From that position, you know that the distance from the origin node A to the node you are now, which is also A, is 0. So, we can complete that information in the table now. Since you haven't started the traversal of the graph yet, you don't have information about the rest of the nodes. So, as far as you know, the rest of the nodes are at an infinite distance from node A. So, we can complete that information also in this table. Let's move to the third column. This column has the information of the node you are coming from when arriving at the destination node. This is why this column is called previous, because it stores the information of the node previous to the destination node if you were following the shortest path route. In the case of node A, the previous node is node A itself, so we record that information on the table. For the rest of the nodes, we don't know yet. So, with this initial routing table, we complete the first step of Dijkstra algorithm. The next step consists on initializing the set of unexplored nodes. At this moment, none of the nodes has been explored, so the set U contains all nodes of the graph. And then we execute the third, final and longest step that is in charge of updating the routing table. To do so, each node in the graph is analyzed. These instructions are in charge of selecting the next node to analyze. Once analyzed, it is removed from the set U and never considered again. Once a node is selected to be analyzed, this for loop is in charge of checking whether a route passing through this node immediately before reaching destination is better than a previously recorded one. We will see how this specific for loops works with an example now. We will simulate the execution of these steps, assuming that we are running Dijkstra's algorithm using node A as the start node. Here, you can see all the steps of the Dijkstra's algorithm together. I have used node A in some lines of the algorithm because in our example, this will be the source node. If you want to run Dijkstra's algorithm using another node as the source node, you need to change A in those lines. We start by initializing the routing table. In this case, the only row with useful data is the row corresponding to the starting node. We know that the distance from A to A is 0 and that to get to node A, you previously visit node A. It sounds strange, but it's going to make more sense with the rest of the nodes, where there is actually a route, understood as a sequence of nodes connected by links. Next, we initialize the set of unexplored nodes U. At this moment, none of the nodes has been explored, so the list contains all graph nodes. Now, we check the condition of the while loop. Are there still elements in U? Yes, there are. So we execute the instructions inside the while loop. First, we select the node from U that has the minimum distance to the source node A. To find out what node is this, we look at the routing table and identify that this is node A. Next, we will process each neighbor node of A that it is in U. These nodes are B, D, and E. Let's start processing neighbor node B. We must calculate the distance from the source node A to the neighbor node B by using the route that passes through 8. This is the distance from A to A plus the distance from A to B. In this case, this is equal to 0 plus 1. So we now know that the route that goes from A to B passing through A has a total distance of 1. Now, we check whether this distance is shorter than the distance recorded in the table from A to B. Yes, 1 is less than infinite. So we update the table with the shorter distance just found and the information about the previous node A, which is A. Which is A. With this, we finish the processing of the neighbor node B and move to the next one. We move now to process node D. We calculate the distance from the source node A to the node D by using the route that passes through A. That is, the direct link between A and D. This distance is equal to 6. Now, we check whether this distance is shorter than the distance recorded in the table from node A to D. Yes, 6 is shorter than infinite. So we update the table with the value of the shorter distance just found and the information about the previous node, which is A. We finish the processing of node D and we move now to process node E. We calculate the distance from the source node A to the node E by using the route that passes through A. This distance is equal to 2. And we check whether this distance is shorter than the distance recorded in the table from node A to node D. Yes, 2 is shorter than infinite. So we update the data in the routing table with the distance just found and the information about the previous node, which is A. There are no more neighbor nodes to process, so we end the for loop and remove node A from the list of unexplored nodes. Before moving to the next unexplored node, let's have a look at the updated information on the routing table. The information in the first row means that the distance from the source node A to node A is equal to 0 and the previous node along that route is node A. The information in the second row means that the distance from the source node A to node B is, with the information collected so far, equal to 1, and the previous node along that route is node E. So we can deduce that there's a direct link from A to B with weight equal to 1. The information in the third row means that the distance from the source node A to node C is, with the information collected so far, equal to infinite. That means that at this stage of the algorithm, we haven't found yet a route from A to C. The information in the fourth row means that the distance from the source node A to node E is, with the information collected so far, equal to 6, and the previous node along that route is node A. That means there is a direct link between A and D whose weight is equal to 6. Finally, the information in the last row means that the distance from the source node A to node E is, with information collected so far, equal to 2, and the previous node along that route is node A. That means there is a direct link between A and E whose weight is equal to 2. Now, let's continue with the execution of the algorithm. The condition of the while loop is true, so we execute the instructions inside it. We select the next node in U with minimum distance to the source node, which is node B. And we identify the still unexplored neighbors of B. They are nodes C and D. Let's start with node C. We calculate the distance from the source node A to the node C by using the route that passes through B. From the routing table, we already know that the distance from A to B is equal to 1, and from the graph information, we know that the link BC has a weight of 2, so this distance is equal to 3. Next, we check whether this distance is shorter than the distance recorded in the table from A to C. Yes, 3 is shorter than infinite, so we update the table with the new distance and information of the previous node B. We move to the next neighbor of B, which is node D. We calculate the distance from the source node A to node D by using the route that passes through B. From the routing table, we already know that the distance from A to B is equal to 1, and from the graph information, we know that the link BD has a weight of 7. So this distance is equal to 8. We check whether this distance is shorter than the distance recorded in the table from A to D. No, 8 is greater than 6. So this new route passing through node B is not better than the previously recorded one. Thus, we do not update the routing table. Since there are no more neighbor nodes to process, we end the for loop and remove node B from the list of unexplored nodes. We go back to check the condition of the while loop, which is true. Thus, we execute the instructions inside the while loop. We select the next node in U with minimum distance to the source nodes, that is node E. And we identify the still unexplored neighbors of E. In this case, it's only one node, node D. We calculate the distance to get from A to D passing through node E. From the routing table, we already know that the distance from A to E is equal to 2, and from the graph information, we know that the link ED has a weight of 3, so this distance is equal to 5. We check whether this distance is shorter than the distance recorded in the table from A to D. Yes, 5 is less than 6. So we update the table with the new distance and the previous node used to get to D using this shorter route. There are no more neighbors of E to process, so we end the for loop and remove node E from the list of unexplored nodes. We go back to check the condition of the while loop, which is true, so we execute the instructions inside it. We select the node in U with the minimum distance to the source node A, which is node C. We identify the still unexplored neighbors of C. In this case, it's only node D. So we calculate the distance to get from A to D passing through node C. From the routing table, we already know that the distance from A to C is equal to 3, and from the graph information, we know that the link CD has a weight of 1, so this distance is equal to 4. And we check whether this distance is shorter than the distance recorded in the table from A to D. Yes, 4 is less than 5, so We update the table with the new distance and the previous node used to get to D using this shorter route. There are no more neighbors of C to process, so we end the for loop and remove node C from the list of unexplored nodes. Now we will enter for the last time this while loop. We select the node in U with minimum distance to the source node A, which is node D. But D has no neighbors that have not been explored. Thus, we end the for loop, remove D from U, and the algorithm finishes as the condition of the while loop becomes false. Now, the routing table is complete and we can obtain the length of the shortest path from node E to any other node in the graph just looking at the number in the second column. For example, the shortest route from A to D is 4. Now, if we want to know what nodes make this route, we need to read the information in the third column. In doing so, we get the route backwards, since the information in the table stores the previous node. In this case, of the route from A to D, we look at the previous node of node D, which is C. We move to the row of node C, and we can see that the previous node is B. We move to the row of node B, and we see that the previous node is A. So the route from A to D is A, B, C, D. With this example, we finish our understanding of the idea behind Dijkstra's algorithm. In the next lecture, we will study its pseudocode.